This video will explain the solution to question 13 of the tutorial. You can access the solution to different parts of this question through the video description below. In a computer game played by a single player, the player has to find the path through a maze. The first time she plays the game, the computer shows a simple maze. The probability that she succeeds in finding the path through the maze is 3/4. On subsequent occasions, the maze shown depends on the result of the previous game. The probability that she will succeed depends on whether she succeeded or failed in the previous game. Therefore, we might consider a tree diagram to help us see the outcomes and probabilities involved at each stage. The player plays 3 games altogether, and for each game, she either succeeds or fails. Therefore, our tree has 8 branches. We have drawn the entire tree for your understanding, but to save time, you might only draw the branches you need to calculate the required probabilities. In part 1, we are asked to show that the probability of succeeding in all 3 games is 27 over 512. The only relevant case is the topmost one. We shall now calculate the probabilities along this branch. The probability of succeeding in the first game is 3/4. Subsequently, if she succeeded in one game, the maze becomes harder, and the probability that she succeeds in the next game is 1/2 of the probability of success in the previous game. Therefore, the probability that she succeeds the second time is half of 3/4, which is 3/8, and the probability that she succeeds the third time is half of that, which is 3/16. To find the probability that she succeeds in all 3 games, we multiply 3/4 times 3/8 times 3/16 to get 27 over 512. In part 2, we are to find the probability that the player succeeds in exactly one of the games. There are 3 branches where she succeeds in exactly one game, which are indicated with the red arrows. We will need to calculate the probability for each case. Let's begin with the case succeed, fail, fail. From part 1, we know that the probabilities of succeeding are 3/4 for the first time and 3/8 for the second time. Therefore, the probability that she fails the second time, given that she succeeded the first time, is 1 minus 3/8 equals 5/8. Since she failed the second maze, she is given a simple maze again, so that the probability that she succeeds in the third game is reset to 3/4. Therefore, the probability that she fails the third time is 1/4. Hence, the probability of the event succeed, fail, fail is 3/4 times 5/8 times 1/4 equals 15 over 128. We can proceed in a similar manner to find the probabilities for the other 2 cases, fail, succeed, fail, and fail, fail, succeed. Pause the video clip at this point and try to work out the probabilities on each branch of the tree. These are the probabilities along each of the branches of the tree. Did you calculate them correctly? Since these are mutually exclusive cases, the probability that she succeeds in exactly one game is the sum of the probabilities of these 3 cases. Adding up the 3 probabilities, we get the answer 9 over 32. In part 3, we are to find the probability that she does not have 2 consecutive successes. There are many branches where the player does not have 2 consecutive successes. Therefore, it is easier to use the complement method and first find the probability that she has 2 consecutive successes. These are indicated with the blue arrows. We can calculate the probability for the first 2 cases together. Since we have 2 consecutive successes in the first 2 games, the third game's outcome does not matter. The probability of the first 2 cases together is 3/4 times 3/8 equals 9 over 32. The probability of the case fail, succeed, succeed is 1/4 times 3/4 times 3/8 equals 9 over 128. Therefore, the probability of having 2 consecutive successes is 9 over 32 plus 9 over 128 equals 45 over 128. By the complement method, the probability of not having 2 consecutive successes is 1 minus 45 over 128 equals 83 over 128. Part 4 is a question about conditional probability. We have to find the probability that she has 2 consecutive successes, given that she has exactly 2 successes. Let us denote the event that she has 2 consecutive successes as A, and the event that she has exactly 2 successes as B. Then we can write down the conditional probability and this formula. We will need to find probability A intersection B and probability B. The event A intersection B can be interpreted as having 2 consecutive successes and exactly 2 successes. The only cases that exist in this event are succeed, succeed, fail, and fail, succeed, succeed. On the tree diagram, the red arrows indicate event A, 2 consecutive successes, and the blue arrows indicate event B, exactly 2 successes. Since we only require events A intersection B and B, we can remove the red arrows and indicate the cases in the intersection with yellow arrows. With this, we can calculate the probabilities of each of the 3 cases, and hence find probability A intersection B and probability B. Adding up the corresponding probabilities, we find that probability A intersection B is equals to 153 over 512, and probability B equals 333 over 512. Hence, applying the conditional probability formula, we obtain the answer 17 over 37.